It's pretty awesome.
Last class we talked about rolling smoothly. Okay. Rolling smoothly is rolling without any slipping. It happens when the static frictional force is large enough to prevent the sliding. Okay, so then you have what happens is that at the bottom point, the contact point here, the translation, the velocity comes from translation. We exactly cancel the velocity from the rotation, because if it's in rotation, it will produce some tangential velocity here, right? Okay. And on the other hand, the whole object is moving with some velocity, okay, to this direction. So if they cancel each other exactly, this is rolling smoothly. And mathematically, we can derive a condition for rolling smoothly. You can think about this. It asks the two velocities cancel each other. One velocity is the velocity of the body as a whole. So it should be the same as the center of mass velocity. Okay, so that's the velocity of the translation for the object as a whole. And on the other hand, this velocity, the tangential velocity produced by the rotation, we know it's related to the angular velocity, right? So V equals to omega r, right? R is the radius of the wheel. Omega is the angular velocity for the rotation. So if this is to cancel this, then we immediately get VCOM should equal to V. Okay, the two should have the same magnitude, equals to omega r. So that gives us the condition for rolling smoothly, which is the center of mass velocity should be the same as the tangential velocity for the rolling, for the rotation. Okay. And we can further get this one. If this is true, this must be true. The center of mass acceleration then has to be the same as angular acceleration multiplied by the radius. This quantity is actually the tangential acceleration produced by related to the rotation. Okay, so the two has to be the same each other, so they can cancel each other. Okay. So that's the condition for the rolling smoothly. Physically, rolling smoothly happens when the static friction is greater enough to prevent the slippage. Okay? Any question here? Now, let's go back to take a overall about the frictional force we have for different situations. For the moving object, okay, for any moving object, it's in a sliding motion, okay, then you will have the kinetic friction. That's a friction usually, if you are trying to move something, that's a friction you have to overcome, so that's bad stuff, okay, it's a bad guy. For the rolling, the situation is more complicated. You may have many different kinds of frictional force, okay? Not all of them are bad. Think about if you have a rolling object, okay? So, even this is a moving object, you will definitely, in your car, have the static friction, okay? And by the way, the static friction is the good stuff here. You need the static friction to maintain the rotation of the wheel. Without the static friction, you cannot even rotate your wheel. Okay. or if you can rotate it, but it wouldn't produce the motion for the whole car. It's just like if you just rotate your wheels on the ice surface, it wouldn't make your car to move. So the static friction is actually good, and it doesn't. You don't have to overcome the static friction, okay, to move the car. So that's the force to help you to move the car. But on the other hand, once the wheels start to rotate, okay, then you are going to have the so-called rolling friction. Okay, it's just similar to the kinetic friction. It's kind of kinetic friction, but it's not sliding friction. It's rolling friction. The good thing about the rolling friction is that it's much smaller than the kinetic friction. So it's bad, but since it's small, so that's why we want to use a car instead of just pull object like this. Okay. Of course, if you want to further reduce the friction, I think we talked about this before. How can we kill the even the rolling friction? This is more, but if you want to kill the rolling friction, what should we do? Then we have to completely remove the contact between the wheel, okay, and the track, okay. But of course, by that time, you don't even have the wheel. The wheel is meaningless. You don't have any contact frictional force. So we talked about these things before, but I go to the website of internet to find the precise parameter for the maglev train. Okay. So far, there is only one commercially operated maglev train in Shanghai. It's a very short road, serves from airport to the downtown. Okay, it's just a kind of experimenting stuff because it costs a lot to build this kind of train. So the top operational speed is 286 miles per hour. Okay, and the top test speed for this train is 311 miles per hour. Okay, so it's quite fast, as I mentioned. If you take the airplane, you probably notice that. Okay, I don't know, some airplane will display the speed, the ground speed of the airplane on the back on the TV. So I don't know if you have noticed that. Most of the time, it's about 500 miles per hour. Okay, so this is more than half of the airplane speed. But this is, in fact, it's called, okay, that's a picture for that train. It's called a conventional maglev, okay. And the future direction is to, okay, so-called a high temperature superconducting maglev. The difference here is that what kind of magnet you are going to use, okay. How do you produce this magnet? For this train, we are using the normal electromagnet. Okay, so if you make some if you have the current goes through some object and then you can produce the magnet. Okay, so that's a normal magnet you have. Another way to produce the magnet needed for maglev is to make the superconductor. Okay, the superconductor is something for many material like the normal metal. If you cool it down to some temperature, below some temperature, the normal conductor will become the superconductor. The superconductor, the special thing about superconductor is that then you don't have any resistance. Okay, so when you propagate the current, you don't have any energy loss. So that's a very good thing about superconductor. Superconductor, for many years, it has been one of the most important research direction for modern physics. I'm also in this kind of area. So because one thing, it can propagate the current without any resistance. So it can be used for power transmission, electric power transmission. And on the other hand, once you have the superconductor, it will automatically becomes a very good magnet. Okay, it can be used for all these things like maglev. Okay, so the so-called high temperature superconductor means, okay, we say that we have to cool the material down to some temperature to transform it to superconductor. So of course, if the transition temperature is high, then it's easier to do this job. Okay. For the normal metal, the transition temperature is really low. So it takes you a lot of effort to cool it down to that temperature. And high temperature superconductor is easier to do. In fact, we can even do it in our lab. Many of those high temperature superconductor, if you put them in the liquid nitrogen, then it becomes a superconductor. Okay. So far, the first reported crude high temperature superconductor maglev was tested in 2000 in Chengdu, China. Okay, I mean, if you remember, Chengdu is my hometown. And by the way, it happens that I know the one who ran this test, who in charge of this test. I happen to know that. In fact, it's a relative of my family. It's quite far. It's kind of the uncle of my brother-in-law. Okay, so I don't really know him, but he's in charge of this kind of test. So far in the internet, we couldn't find any detail about this test. Okay, it's secret. Okay, kind of national secret, because it definitely has a military application. Okay, but probably if I met him, I can ask to see if he can give me some information. So that's rolling friction. Okay, and for us, we talk more about the rolling smoothly. So there is nothing for us to consider. How can we get rid of the rolling friction? We are starting the rolling smoothly. In that case, okay, we are thinking more about what's the condition to produce this kind of perfect rolling. Okay, so this is very important information you need to know about.